recording? Okay, so we're going to continue on in our discussions here. We've got kind of a new section or something, I don't know. We've got EM type optimization. Okay, so have you guys learned the EM algorithm in other classes? Yes, no, maybe? Okay, so this is a, so EM, E stands for expectation, and M stands for maximization. Okay? And so basically, this can be applied in different situations, and it's an iterative process where you try to you're kind of maximizing based on there's kind of like two maximizing steps that you're iterating between. Okay, so we'll first start off with a simple version of this. Okay, so simple EM type algorithm. Because the actual EM algorithm is a little bit different, but this is like a EM type, all right, and this is called k-means clustering. Have you guys heard of this before? Maybe? Okay, k-means, that's clustering. We want clustering. Okay, I'll say not to be confused with k nearest neighbors. Okay. And the idea is, you know, let's say, let's keep it simple, and let's say we have two-dimensional data, x1 and we have x2, okay, and we have data that comes from one cluster, and they're located here, and then we've got data in another cluster. Okay. And so, you know, we would say, you know, our data matrix X is equal to Xij, okay? And these are, they exist in k subgroups, or we'll just say k groups. Okay, and to us the group membership is unknown. Okay, okay, and we wish to group them. Into k groups. Okay, and so group membership or, you know, a cluster label is given by Z. Okay, so Z is a vector of cluster labels going from Z, from 1, Z2, all the way up to Zn. Okay, so we have, you know, n observations and p basically variables. Okay, so we've got, so in our case we've got two p's, so we got an x1 and an x2, okay, and then we've got n observations. Okay, so z sub I will equal 1, 2, up to k for however many groups there are. So in our case, there's only 2. Z can either be 1 or 2. And it's just a cluster label of basically the ith observation in X, okay? Okay, all right, and so in this case, we are pretending to actually know what we have. All right, and so here, we've got kind of this circle of points. These points have z sub I equal to 1, okay? And these have z sub I equal to 2, okay? So in this case we have k is equal to 2 in this case. All right, but when we look at the data, we don't actually know the cluster labels, all right? So how can we label our data? What can we do to label our data? Okay, so when we get our data, basically all we have are just, and this is a very easy example, okay, where we can just kind of look at this, and so our eyes are pretty good at creating clusters in 2 dimensions, okay? So we can look at data and we can say, oh, I see some clusters very easily, all right? Our eyes are very good at this. But, in higher dimensions, we'll have trouble kind of visualizing this, and can we train a computer to kind of form clusters for us? That's kind of the idea here, okay? So what the k-means clustering algorithm does, okay? What k-means clustering does is basically you specify a k. You say, try to fit 2 clusters or try to fit 3 clusters to our data or something like that, okay? And what it's going to do is, so we try to fit k clusters to the data, okay? And we try to minimize the total squared distances, or we might abbreviate this the TSD, okay? That's what we're trying to do. So basically, what you do is we're going to each group, so if we have k clusters, each cluster has a group mean mu sub k, all right, has a group mean mu sub k. So group 1 is going to have its own k, and group 2 will have its own k. And basically, I'm going to make a few copies of this so we can kind of see like how this would work. okay? So if I, so each group has a mean mu sub k, and then what we're going to try to do is we try to minimize the total square distances. So the total square distances will be defined as this, which is going to be the sum of each x sub I from the group that it belongs to. We're going to add this up, and this is for all i's within some z sub I that is equal to k. So basically this says, you know, add up the total distances for, you know, all the points in group 1, add up all the total distances for all the points in group 2, and add those together, okay? So basically, you know, add all the distances, all the square distances for all points and for all groups. Okay, and so, you know, we're gonna try to minimize the total square distances, which is a function of z being our group membership and the location of mu. Okay, so minimize the total square distances. This is a function of z, the group membership, and mu, the group means. All right, so we can think of this as for all from k equal 1 to k, I guess I should use kappa, and this is for all the points within a group. Okay, and so so essentially, let's say you just start off with two kind of. Let's say this is just an initial, these are my initial, it could even be terrible, all right? So we can, let's say these are my two initial starting points for mu sub 1 and mu sub k, or mu sub 2, okay? So this is, these are my starting points here, okay? And then so, you know, basically I've got two steps that I iterate. Okay, step 1, basically assign points to the nearest, or I'll say to the group with the nearest mean. Okay, and this, we can essentially think of this as set z sub I equal to you know, the z sub I that minimizes okay. So basically, just, you know, for each data point, you're going to set it to the group that minimizes this. Okay, so, you know, if I go through this, all right, you know what? I'm going to label this mu2 as a red dot. Okay. Okay, so I'm going to look at this and I'm going to say, okay, is this point closer to here or closer to here? It's hard to say. So I think this one becomes red. This one I think is closer to the blue. I think these ones are all closer to red. Is that right? It's kind of hard. I chose these bad points. But I think, you know, looking at this, this looks like, so is this, so I think these are all closer to the red point than they are to the blue point. I'm just kind of eyeballing this, right? So it looks like, in this one, which one is this closer to? This data point, is that closer to the red or the blue? What do you think? I'm going to say red. And this one, I'm also going to say red, okay? But it looks like these ones are closer to the red than they are to the blue. Okay, and so what we have here is these ones are closer to blue. It's hard to say. And I think this is what we get kind of at this point. I don't know if you guys agree with me or not, okay? It doesn't really matter, all right? Okay, so this is kind of like, so this is our initial step, right? So, you know, we started off with an initial mu1 and a mu2, and basically, based on these locations, you're gonna go through your data, and you're gonna assign the data points, the z, so you're gonna say, so all of these red ones are gonna have z equal to 2, and all of these blue ones will have z equal to 1. Okay, so you go and you set all of your data to have this, okay? And then now, based on this, step 2 is you, given the value z, update the centers, okay? Update the centers so that they're basically in the center of your data. So you're minimizing the total square distance, okay? Update the center to minimize total square distance, which is essentially going to be set your mu sub k equal to 1 over n of basically adding up all of your x sub i's, okay? For everything that belongs in, you know, where I has group membership z equal to k. Okay, so in our second step, basically I have, you know, I said something like, these are my blue, and these other ones are kind of the red. So this is what I have in the second iteration. And then so what's going to happen is with these data points, the new center is going to go right in the middle of all of these data points, okay? So this is now my updated mu sub 1, okay? And then over here, I've got to kind of find, you know, where's the middle point over here? It's probably going to be somewhere like right here. Do you guys agree? Something like this? Okay. So this is, so after assigning all of the values, we say, okay, we're going to look at these and we're going to find the mean of kind of these circles of points, okay? So, you know, where's the mean? So this is, you know, our update, we update our means. Okay. All right, and then we just repeat the process again, okay? And do you guys have this down? Do I need to give you another? Okay. Let me see. Maybe I can shrink this a little bit. Let's fit here. Okay, so now copying just kind of the location of this thing. So I think the blue dot is right there, and then the red dot is now right here. Okay, now I go back and I do this step again, which is going to be, assign all of the points to blue. All right, and we ask, which, and so all of these points are now much closer to the blue dot than they are to the red dot. And then, all of these are much closer to the red dot than they are to the blue dot. So, just after 2 steps, we've essentially clustered them, okay? Like I started off like this, and then just after 2 iterations, or just 1 full iteration, on the next one, we've already successfully clustered these into their respective groups. Okay. Is this okay? Yes.
How do you take the positions of V1 and V2 to the very first
These two?
Yeah, like how do you know to set
No, these are just random initial points.
Okay.
So I'm just saying, you're gonna start off with your data, you just start off with 2, you just pick 2 random points, mu1 and mu2, okay? And based on mu1 and mu2, you just start assigning these points, and you say, okay, this point right here, is it closer to the blue dot or closer to the red dot? Looks like it's closer to the blue dot. I don't know, okay? I'm just eyeballing these, and maybe if we measured them, we're wrong, okay? Is this dot over here closer to the blue dot or the red dot? We say it looks like it's closer to the red dot, okay? And then we do that for all of these data points, okay? Then we get these clusters. So we've got a separation here, and we say, okay, since these ones belong to team blue and these are team red, find the middle of team blue, find the middle of team red, okay? Now that we've done that, we're going to go back and we're going to look at our labels and reassign the labels. And then you just keep doing that until you converge somewhere, okay? And then so, in our next step, we're going to our dot is going to move to the center over here, and our dot's going to move over to the center over here. And then essentially the algorithm has converged there. Okay? So this is EM type algorithm because there is kind of a quote E step, which is where well, actually, I think our M step came first, but so basically, you're just iterating between 2 steps where, one is assign class labels or cluster labels based on which mu sub k is closer. And then 2 is, now that we have cluster labels, update locations of mu sub k. All right. So this is going to minimize your total squared distance, okay? So, and then you just iterate, okay? Repeat. So update the locations of mu sub k, update your cluster labels. Update your, keep going back and forth between updating the locations of mu sub k and updating your cluster labels. And so, we can think of one of these as kind of a maximization step and one of these as an expectation step. So we can kind of think of this as kind of like an M step. We're trying to maximize our data likelihood okay, by, you know, changing class labels, okay? And then this can be thought of as kind of an E step. You know, what are the expectations expected values, kind of our centers based on current class labels. This is not an official EM algorithm. It's related, but it's an EM type. Okay. All right, and so this algorithm will minimize the total squared distances between points and their, I guess their cluster's center. Okay. Kind of a, this is probably not the best algorithm to use for clustering though, okay? And there's shortcomings of the k-meanings algorithm, okay? I think it's a good algorithm as kind of an introductory algorithm to this concept of kind of EM type algorithms, in that I feel like it's easy to understand what's happening, right? Okay, so you know it's easy to kind of understand what's happening, but there are some shortcomings, and one is that it's assuming that shortest distance is the best way to classify your data, okay? So basically, the primary assumption, the biggest assumption of this algorithm is that shortest distance best way to classify a data point, okay? Are you guys familiar with Voronoi diagrams? Okay, so a Voronoi diagram basically, you know, you've got some kind of space here, and you know, given two centers, or given some centers, what it's going to do is it partitions the it partitions your space so that you know, everything in this zone is closer to this point, and everything in this zone is, you know, it partitions your diagram or your space based on shortest distance, okay? Partitions a space based on shortest distance, okay? So, you know, if you've got two centers, it's going to partition it like this, and so any data point on this side of the line is going to belong to this group. Any data point that belongs to this side of the line is going to belong to this group. Okay, so essentially, and so basically when I did this, essentially with these two data points, I essentially drew kind of like a path right there that said any of these data points that are on this side of the line are closer to this one, any data points that are on this side of the line are closer to this point. Okay, so Voronoi diagram just basically partitions a space based on closest distance. And so, you know, it forms kind of like these nifty little patterns. If you've got multiple centers, so let's say you've got like four things, it's going to say like, okay, it's going to draw kind of a line here, and then it's going to look at this over here, and it's going to say like, okay, something like this. And I'm eyeballing this, so I don't know if this is any good, but it does something like this, okay? And it's going to say, okay, values that are closest, these lines kind of distinguish and say like anything over here is closest to this center, anything over here is closest to this center, and things like that. So we have, we're partitioning based on shortest distance. I should just Google Voronoi diagram. This is going to give us better pictures. Okay. Oh, look at this is a fancy one. Look at that. Okay. Of course, from Wikipedia. So here's, there's 20 points, and, it says, based on this, these are the closest distances to the thing, okay? And so this is how the k-means clustering algorithm is basically going to end up partitioning your space, okay? Well, essentially, your initial starting point, it's going to do this, and then it's going to cluster based on these things, and then it's going to recalculate the centers of these things, and it's going to proceed that way. They're interestingly, oh man, I wonder if I could find this picture. Reese's cup Voronoi. Reese's cup. Oh yeah, look at this. This is what we have here. Like, okay, so see, this is a Reese's peanut butter cup. I don't know if you guys, can you guys see the little, the things there? So basically, what this is telling us is that, when the chocolate is being filled onto the Reese's peanut butter cup, there's probably like a little nozzle right here, right here, right here, right here, and because, the way chocolate comes out and it fills out kind of at this even space, you're going to get these boundaries right where they're equidistant from each other, and so you get this funny Voronoi looking diagram on top of your Reese's peanut butter cup. Okay, that's cool, right? All right, so anyway, that's a Voronoi diagram, and basically a k-means clustering just it takes your initial starting centers, it partitions your space based on that, then it reassigns. Once it reassigns those centers, it recalculates the mean, and it does that, okay? So here, the problem with this, actually, I'm sure Wikipedia has a good, let me see, k-means clustering mouse. Where's the, yeah, okay. So this is the problem with, if you do k-means clustering on data like this, okay? So probably the original data, we've got this thing going on, all right? So this is, all of this data belongs to the green group, this belongs to the blue group, this belongs to the red group. Can I copy this image? Oh my gosh, what is this? So, you know, we want to do something like this. K-means clustering assumes that nearest distance is the best way to go, okay? And so what ends up happening is it ends up grouping this over here, and this over here, okay? And so you can kind of see a little bit of the boundaries. How do I copy this? Oh, no. Okay, well, I guess that's okay. Okay, so I'll just use this. So, you know, you can kind of see the boundaries forming something, you know, something like this, okay? And then so you've got the center over here, and the center over here, and the, you know, the center over here, okay? But this is obviously not the best solution, okay? You know, our eyes are pretty good, and I think we can pick these things out quite well, right? Based on our whatever, the visual processing system that we have in our brain. And I think when we look at this, we can say, oh, this is probably not the best system. So this is going to be k-means. And the problem is that, you know, shortest distance is, you know, not necessarily the best solution. Okay, this over here is a proper EM algorithm. Okay, so let's, well, I don't know if I'll have time to actually talk about the EM type algorithm. Let's see. Okay, but if, well, I mean, the answer is yes. It would be easy to do. So, you know, if I'm trying to think if we want to have one more homework assignment, or just, you guys are shaking your head. Okay, so, all right. All right, so, well, okay. Then, you know, maybe as part of a final exam task would be to write up the k-means clustering thing. And I think it's pretty straightforward, right? You need to write a function that calculates the distance, and then you basically just say, like, okay, calculate the distance from this data point to, you know, the current means that exist. Pick the one that's the closest, assign it to that. Okay, so I think it's a simple, straightforward task to write a k-means clustering algorithm as an assignment. All right, and then I guess I'll start talking about the EM algorithm, and then we'll get into it a little bit more in depth on Friday. Something exciting is going on out there. Yeah. Okay. Well, maybe I'll just talk about some applications of k-means clustering. So, okay. So if you look at, like, if you take an image, right, and an image might have, like, you know, with our current system of RGB, you can have like several million colors, right? But then if you want to trim that down to like a GIF, you're limited to 256 colors, okay? So how do you pick which colors you should use, okay? K-means clustering can help in that, you know, you say, I want you to find 256 clusters of colors, okay? 256 basically pick out the best 256 colors to use here. And so you can just take the existing color set. Okay, here, let me see if I can illustrate. All right, so k-means clustering for color selection. Yeah, whatever, okay. You know, so you maybe you list off all of the colors that exist in your image, okay? And you graph these based on your RGB values, all right? So, you might have several million colors show up in your thing. Well, with k-means clustering, you can say, okay, pick out the best 256 colors that show up in this thing, and it's going to, cluster, these 1,000 images, or these 1,000 colors, these just tiny subtle shade differences between slightly light green and ever so slightly lighter green, okay? So you've got, thousands of shades of green, and it's going to cluster those shades of green into light green, okay? And it's going to take, these thousands of shades of blue, and it's going to cluster it into, blue. And you can thus simplify, multi-million color image into, a couple hundred colors of images through k-means clustering. Okay. So, that would be a good application for that. Whereas, and k-means clustering is pretty good if this shortest distance thing is a safe assumption. If shortest distance is not a safe assumption as a way to partition your data, it's not a good method. Okay, so we'll say next time we'll do an actual EM algorithm, which is, this is more a probability-based algorithm. Okay, so we'll look at Gaussian mixtures. Okay, and so what we have with Gaussian mixtures is your data. You've got some normal distribution here, okay? So this is a two-dimensional normal distribution, and it's generated a bunch of data points here. Okay, you've got one, so this is data from a multivariate normal. And then you've got another, and maybe we'll have some overlap. Oh, okay, these are supposed to be better looking. All right, and then you got data from another normal distribution, right? So each of these are generating in two dimensions, x1 and x2. Based on what we see here, can we distinguish which data belongs to this cluster over here and which data values belong to this cluster over here? Okay, this is the question that we're going for. Okay, can we successfully cluster our data, okay, and all we're doing is we will assume our data comes from a mixture of normal distributions. Okay, or this is called the Gaussian mixtures. Okay, and obviously, if you have different types of mixtures, things will be different. But this is a problem with a lot of history behind it. This, the heights of humans can be thought of as a Gaussian mixture between a normal distribution for male heights and a normal distribution for female heights, right? That's only one dimensional, okay? So, you know, can we categorize who's male and who's female based on height? Kind of, but you're limited to one dimension, so you're just going to have a single cutoff, okay? But maybe we can mix something else in. We can mix in body fat percentage or something. I don't know what comes as a normal distribution. I have no idea. But if we look at body fat percentage, it's also a little bimodal, right? So I don't think I'm saying anything wrong by saying statistically women have a higher percentage of body fat than men do, okay? And so if we take into account height and we take into account body fat percentage, can we distinguish who is probabilistically likely to be male and who is probabilistically likely to be female, okay? And of course we're going to have, this is not going to be a perfect way to distinguish who is a man and who is a woman, but you know, our data might provide some insight this way, okay? And it might be possible, maybe not, okay? I don't actually know if I have data on heights and body fat percentages, but it would be an interesting problem, and you know, we got questions like this for all sorts of different stuff, okay? So that's what we'll do on Friday, and so until then, we'll see you guys later.